Welcome to Etale Cohomology on November 24th, 2020. So we're going to continue with proving the Riemann hypothesis for varieties over finite fields today. So let me briefly remind you where we were. So last time we finished, at least for now, discussing the Grothendieck-Lefschetz trace formula. And let me just briefly remind you what that said, and then we will kind of continue with the proof of the Riemann hypothesis. Okay, so what was the upshot of the discussion last week is that modulo a couple things that I'd punted. There's in the following situation. So this was the theorem. So if you had U naught was a curve over a finite field FQ, and E naught was a locally constant QL sheaf on U naught with L not dividing Q. Then we had the following trace formula, which is a generalization of the Lefschetz fixed point formula, which is that if you sum over the Frobenius fixed points of U, so that's the rational points of U naught, the trace of the Frobenius at X on the fiber of E at X. So here, if they're naughts, it means we're over the finite field. If there's no naughts, it means we've base changed to the algebraic closure. And the claim was that this sum was equal to the sum -1 to the R of the trace now of the relative Frobenius, which I just called F, on the compactly supported cohomology of U with coefficients in E. Okay, so this was the theorem. I didn't prove it, but I sort of which involves some long digression into understanding traces in terms of perfect complexes. And then, so I'm sorry about that?
Sorry, it froze for the last 10 seconds, just FYI.
Yeah, sorry. So what I was saying is that we didn't prove this formula, but I sort of gave everything one needs to reduce it to the case of constant torsion sheaves, which involved a long digression into traces on perfect complexes. And if we have time, we'll come back and finish explaining the proof. But it's given that it's sort of formal from the Lefschetz fixed point formula, although not when I say formal, I don't mean trivial. Okay, and then we made this definition, was the zeta function of U naught E naught T was exp of the sum over M of the sum over X in UF to the M, so the FQ to the M points of U naught, if you'd like, of trace of the Frobenius at Fx on Ex, T to the M over M. So in the case Ex is the constant sheaf, E is the constant sheaf, this is just the usual zeta function of U naught. And then we explained that the theorem implies that the zeta function is rational and can be written in terms of the characteristic polynomial of Frobenius of F on the compactly supported cohomology of E. Okay, so this is just by the exact same proof that the usual zeta functions of varieties are rational. You take the logarithmic derivative of this and compare it using the Lefschetz trace formula to the characteristic polynomial of Frobenius on the cohomology. Okay, so now our goal, let me remind you, is to prove that these rational functions we get in the case where E is the constant sheaf, so just the usual Grothendieck or the usual Weil zeta function, have roots and poles with certain polynomials. So the goal was to show that Frobenius acted on cohomology with eigenvalues, which are so-called Weil numbers. So for any embedding of the field they generated over Q into C, their absolute value is the same, and it's Q to the I over 2, where I is the cohomological degree, as long as the variety is proper. And the procedure we're going to take to do that will be to fiber our variety over a curve and use the Leray special sequence. So we're going to plug in for these E naughts here, the derived push forwards of the constant sheaf along certain fibrations over P1. So today we'll study these zeta function of U naught, E naught, T for certain very special E naught arising from so-called Lefschetz fibrations, which is a way of turning a variety into a family over P1. Because it's the main lemma that goes into the proof of the Riemann hypothesis. We'll discuss it a little bit, and then I'm going to kind of sketch out the entire rest of the proof, and then we'll come back and start proving the main lemma and filling in the details. Okay, so let me briefly explain what I mean by these very special E naught. So these are going to be the hypotheses of the main lemma. So here's the main lemma, which this is a slightly main lemma in all caps because it's extremely main. So these are this is sort of the situation we'll try to get ourselves into. So X naught is going to be a smooth affine genus zero curve. Sorry, genus zero curve here. Curve means geometrically connected. Over FQ. Genus zero won't really be important, but we'll get ourselves into that situation. We'll let X be the base change of X naught to FQ bar, as usual. And we'll have E, a locally constant QL sheaf on X naught. And then this Roman E will be the corresponding representation of pi1 tall of X naught. And I'm going to suppress the base point, but when we have a one representation, there's always a choice of base point. Okay, so this sheaf is going to have to satisfy a bunch of assumptions. So what we're going to assume is the following. So first of all, we're going to assume that for each closed point, so for each X in a set of closed points of X, so here when I write bars around a schema, I just mean the set of closed points. The Frobenius action on the fiber of E. So another way of saying this is this point gives you a conjugacy class of Frobenius in this group, as discussed last time, and that conjugacy class acts on this representation. And so this action here is conjugate to that action that I just described. So for each point like this, we're going to assume that the characteristic polynomial has rational coefficients. Okay, so that's assumption one. Okay, assumption two is that there's a non-degenerate skew symmetric form going from E times E to QL of minus N. So ultimately, this is going to come from the couple. So what do I mean by this, by the way? So I mean, these two things are representations. This is also a representation. It's not a very interesting one. So this factors through the Galois group of the ground field. So let me remind you, this is the cyclotonic character tensor powered to the minus n times. So you dualize and take it to the tensor power n. And skew symmetric means that if you pair A and B together, you get minus. You pair B and A. Okay, and non-degenerate means that for anything you plug in here, there exists something you can plug in here to make the pairing non-zero. Okay, and then finally, if you restrict the representation E to pi1x, so that's a subgroup of pi1x naught. So this thing maps to, it maps to GLE. That's what it means for your representation. But in fact, it lands in let me give this pairing a name. In fact, this lands in the symplectic group of this pairing. So why is that? I'm just the definition. This is that preserves the form, and I told you this form has to be kind of it's a map of representations. Or it is a tensor here. So it factors like so. And the hypothesis is that the image, let me call this rho, the image of rho, we want to be open in SP, E, C. So this is called big monodromy. So when one has a locally constant sheaf like this, the representation E is called the monodromy representation. And this is saying that the representation is big image. So in particular, like inside of here, up to some non-uniqueness, there's a copy of SP2G of ZL, where E is 2G dimensional. E has to be even dimensional by the existence of a non-degenerate skew symmetric form. And this is saying that the image has finite index in that ZL subgroup. So this is a very strong condition. Okay, so these are the hypotheses. So before I start saying so then there's going to be some conclusions. But before I start saying the consequences of these hypotheses, are there any questions about the hypotheses?
I don't quite understand too, because the QL minus N is that the Hodge structure?
No, that's a Galois representation, or so
I see.
this is a representation of the Galois group of FQ, and this group surjects onto the Galois group of FQ. So we view it as a representation of pi1 Etale. If you want to, you can also think sheaf theoretically. So it's saying that there's a skew symmetric product on the sheaf E with values in the sheaf QL of minus N, which is just pulled back from the point.
Okay.
Does that answer the question, Ben?
Right, I see.
Great.
So it's the
any other questions? Sorry?
I'm surprised about the genus zero part.
That's not important at all. I mean, we're going to apply it in the case where X naught has genus zero, but it really will not affect the proof. Yeah, so that you can state this for any smooth affine curve. There's the statement would be, well, yeah. It just simplifies the statement a little bit. Are there any other questions? Oh, it's telling me my internet connection is unstable. Can you guys hear me?
Yeah.
Okay,
It's just been cutting out every
I have a question. X is the X bar base extension to FQ bar, right?
Yeah, that's right.
So X is isomorphic to P1 or FQ bar.
So X is isomorphic to P1 minus a bunch of points because X naught is affine.
Oh, okay. Sorry.
Yeah, that's correct. Yeah, yeah. But that's the situation we're in. We're yeah. So let me. I mean, maybe before I continue, I'll spend a lot of time discussing like where this situation will come from in a little bit. But let's just think about where a sheaf like this should come from. What you should imagine is that you have a family of odd dimensional varieties over P1 minus a bunch of points, like a smooth proper family of odd dimensional varieties over P1 minus a bunch of points. So think, for example, of a family of curves. And then you should think E at least is some piece of their middle cohomology. So that has a pairing on it coming from the cut product of classes in odd degree, it's skew symmetric. And then, okay, big monodromy, it's not, if you take a random family, it won't have big monodromy like this, but there's a certain special situation called a Lefschetz fibration where there's a piece of the middle cohomology that's always guaranteed to have big monodromy. That said, I mean, I said that this is a strong condition, but it's also kind of a ubiquitous condition. Like if you, it's not hard to write. I mean, this lemma would not have a lot of power if it was really hard to write down examples of families with big monodromy. So it is like it's a very ubiquitous condition for a family of varieties to have big monodromy on their middle cohomology. And we'll discuss, I mean, for much of today, like how to actually make such families.
It's not just Lefschetz fibrations.
Right. Are there other questions before I?
I'm assuming there's lots of other examples that aren't Lefschetz fibrations that have big monodromy. Okay.
Is a pretty good. I mean, I don't want to make I'm not making a. I'm sorry.
You're cutting out a bit.
Oh.
Yeah.
Let me maybe. Yeah. Let's see. Maybe that will help. Yeah, I'm not making a formal statement here. I just think if you take if you it's if you have if you take a family of varieties, like in general, this is sort of like a vague principle. You kind of expect the monodromy on the cohomology to be as big as it can be, meaning there might be some obvious restrictions, like some cycles, for example, that live in the total space of the family that restrict the monodromy. But morally, one expects it to be big.
Okay, so the opposite situation of finite monodromy is quite special.
Yeah, that's right. That's
okay.
Right. Yeah. All right. Any other questions before I continue explaining the consequences of these hypotheses? All right. So the first hypothesis, or the first consequence, is E has weight N. That means, so this is the same N as the QL of minus N here. So what this means is that the eigenvalues let me just call them alpha of fx on ex have absolute value q to the n times the degree of x over 2, where here for any, this here, x is any closed point. So if you take a rational point, for example, this says that the eigenvalues of the Frobenius corresponding to that rational point on the associated fiber of our local system have absolute value q to the n over 2. So this looks like the middle cohomology of a variety of degree n. It looks like Hn, it looks like what we're trying to prove the middle cohomology of a variety of dimension n looks like. So in general, we expect that Frobenius acts on the middle on the degree n cohomology of a smooth proper variety with eigenvalues q to the n over 2. Here we take x, which is a point of degree d, So Q becomes Q to the degree X, and then we're saying that Frobenius acts on the fiber here via Q to the degree X to the N over 2. And here, when we say has absolute value, here we mean for any embedding of the field generated by alpha into C. All right, are there any questions about this consequence A? Okay, consequence B is that if we look at relative Frobenius acting on the compactly supported cohomology of X with coefficients in E, this has rational characteristic polynomial. And again, and for all eigenvalues alpha, we have that the absolute value of alpha is less than or equal to Q to the N over 2 plus 1. And I think this less than or equal to should actually be a less than. Yeah. And again, into C. Okay, and then finally, we can also push forward to P1. So Frobenius acts on H1 now without compact support of P1 with coefficients in J lower star of E, and we have a similar inequality as rational characteristic polynomial. And all eigenvalues alpha satisfy Q to the N over 2 is less than the absolute value of alpha is less than Q to the N over 2 plus 1. All right. So this is the main lemma. It's more than a page long, so let's take some time to appreciate it. So what you should imagine, and I'll discuss this more in detail, is again that E is the derived push forward of the constant sheaf from some family of varieties over P1. And then you might imagine that something like this, for example, is going to contribute to the cohomology of the total space when you compute it with the Leray spectral sequence. So the sort of thing that will happen is you'll fiber something over P1, you'll compute its cohomology, and then this will contribute. And what you should imagine is that the thing you fibered over P1 has even dimension. And then this will be the middle cohomology of the fiber. So this is the kind of thing that will contribute to the middle cohomology of our even dimension variety. And then this is the kind of what we even dimensional varieties, and this is the kind of inequality we wanted to prove for that. Freddie, I'm sorry, it's choppy. Let me maybe pause for a second and try switching Wi-Fi now.
If you turn off your camera, it might be better. Sometimes the bandwidth doesn't allow that.
Is this better at all?
Yep.
Hopefully that will help. I've switched Wi-Fi networks, so we'll see if that works. All right. So, are there any questions about this main lemma? Okay, so the question now that I want to talk about is where will this E come from? I'll start proving the main lemma after we sketch how we're going to apply it. So where does this E come from? Okay, so the answer is going to be, it'll come from a so-called Lefschetz pencil. But it won't quite be the middle cohomology of a Lefschetz pencil. It will be something arising from the so-called vanishing cycles. So that's something we'll start talking about next time. But today I just want to give you an idea of like what Lefschetz pencils are and where they come from and what kind of properties we'll use, and then sort of the general strategy of the rest of the argument. Okay, so let me make a definition of a Lefschetz pencil. So this is a sort of way of taking any smooth projective variety and fibering it over P1 more or less. And these are, I mean, this is a technique that has a long history. This isn't something that was invented by Deligne. Maybe unsurprisingly, it was, invented by Lefschetz, although I think those ideas predate him and maybe go back to Poincaré. Okay, so suppose we're given X is a smooth projective variety. With X embedded into Pn with via some complete linear system L. So here L you should think is a very ample line bundle on X, and then we've taken all the sections and used them to embed in projective space. So let's take, let's take a line curly L. This is a line inside of the dual projective space. So this is a family of hyperplanes, right? So an element of the dual projective space is a hyperplane in Pn, and this is a linear family of such hyperplanes. So this is a linear family of hyperplanes. Which I'll call HT. So given an element T of this line, we get a hyperplane HT. We say that this is a Lefschetz pencil. If the following three conditions are satisfied. So first of all, one, the pencil, which so the axis, I'll make a remark on that in a second, of the pencil, which we'll call A, and its definition is just, it's the intersection over all the T of the HTs. So this is some codimension 2 hyperplane in Pn, right? So each HT is a codimension 1 hyperplane. If you intersect a one-dimensional family of such, you get a codimension 2 hyperplane. So the first condition is that this A intersects X transversely. All right. So two, and this is but when I say intersects X transversely, I mean like in a scheme theoretic sense. So the intersection of the tangent spaces has the expected dimension, namely the dimension of X minus 2. So two, if we define xt to be the intersection of X with HT, this should be smooth for almost all T. For T in a dense open of L, and 3 so let me call this dense open U of L. For T not in U, the of our line where the intersection is actually singular, then this xt, which is again X intersect HT, is singular, but it's singular in a very mild way. So it has this xt has a unique singularity, singular point, which is an ordinary double point. So let me just remind you what that means. A complete local point is isomorphic to a power series ring in n variables modulo one relation. Well, if that relation was linear, we'd have a smooth point. And here we're modding out instead by a non-degenerate quadric. So these points look like these singular points look like the cone point of the cone over a nice spot. Is also. I think one use as a hard generalization of the following, namely it only has simple ramification. So most fibers are just a disjoint union of points of the degree of the map. So the most fibers are smooth, and then the singular points only have double ramification. They only have a unique branch point, and that branch point is simple. It's double ramification. All right. Are there any questions about? Yeah, sure. So the picture. So yeah, so what we can do is we can sketch a picture of kind of the family, which is so there's a family which is kind of, well, I'll explain this in a little bit, but if we what's the best way to say this? So you can take x times L and then intersect with kind of the family of hyperplanes. So this is the family of hyperplanes. Over L. So this maps to L. I'll explain a little bit more about what this is in a second. And here the fiber over T is xt. So this is the general situation when you have a pencil. You get a family of hyperplane sections of your variety, and so what it looks like is as follows. So here's L. And you have a family of varieties. Most fibers are smooth. But every once in a while, a fiber with a unique ordinary double point. So let's talk about what an ordinary double point is. So let's just say, for example, these fibers are smooth curves. So can anyone tell me what is an ordinary double point if you have a smooth curve?
A node.
Yeah, exactly. It's a node. Yeah, so it's saying most fibers are smooth curves, but then every once in a while you'll get a fiber which is a curve, which is a unique singular point, which is a node. So that's one example. For example, if you want lower, so this is what I was verbally describing. If you have a family of curves, which only has simple ramification at a few points. So here, these are ramification points, and they're all simple. And at any point downstairs only has at most one simple ramification point over it. So this is another example. Another example is you could take a family of quadrics. This is sort of the prototypical example. So take a family of quadric surfaces, and you only ask that you only allow them to contain, like, you only get so you get finitely many quadrics which have rank instead of rank 3, I guess they have rank 2. So that's another example.
Is A allowed to be empty?
So maybe take x squared plus y squared plus t, z squared equals 0. Sorry, would someone asking?
Oh,
something?
sorry. I was asking if the base locus is allowed to be empty.
That is pretty unusual unless I think that basically never happens, right? That'll only happen if you're embedded in P1, right? Because you're taking a line, like the base locus of the pencil is the intersection of a one-dimensional family of codimension 1 things, so it's codimension 2.
Okay.
So it should always get a point. If that's what you're asking.
Okay. Sure.
That is what you're asking about?
Yeah, makes sense.
No, I see. Yeah, I mean, yeah. So, but it's very unusual. So if X here will be embedded, you know, usually kind of positively, and you would expect there to be base locus. Okay, so here's a question: do Lefschetz pencils exist? Like I gave you some examples, and I think this example is kind of the clearest one. So what you should think about. Let me example. Again, we have. Let me just draw this is A1T. So for T non-zero, you get a nice smooth quadric surface. This is T not equal to 0. You get a nice smooth quadric surface with its rulings. Here, I should be maybe working over the complex numbers, so they're really not uncharacteristic too, if I want to write this. Here, what happens at T equals 0? We get a quadric cone. Ordinary double point. Okay, and then again, once you go away from 0, you get these nice smooth quadric surfaces. Great. So what is the virtue of these things? So first of all, they're extremely ubiquitous. We'll see that we'll be able to like basically turn any variety into a Lefschetz pencil in a second, or any smooth projective variety into a Lefschetz pencil in a second. But then the other kind of cool thing about these is that it's extremely easy to compute the monodromy. So we're not going to do this today. Hopefully we'll do it by the end of the class. But the point is all the monodromy on the cohomology is somehow coming, or the interesting monodromy on the cohomology is somehow coming from these singularities. And sort of the part of it that we'll need to compute will be kind of somehow coming from these singularities and computing and one can reduce the computation of that monodromy computations for quadrics, which are very well understood. So ultimately, the point is to reduce some monodromy computations to some computation in this very simple setting. All right. Are there any questions about that? Okay, so here's the main theorem on the existence of Lefschetz pencils. X is going to be smooth and projective. Over an algebraically closed field. And L is going to be. So you might reasonably ask, will there always be a Lefschetz pencil given by taking a line in the dual projective space to the projective space given by embedding X in Pn via L? And the answer in general is no, but yes after replacing L by its square. So then the theorem is that there exists an L, which is inside of the complete linear system L tensor squared, such that L is a Lefschetz pencil. And if we have time, we'll come back and prove it. But the proof is actually not so bad. It's a Bertini argument. It's in SGA 7 actually. It's really nice. And Milne's Etale Cohomology book is a nice sketch too, if you can't wait. But this is really not so bad. The issue, so the reason you might have to replace L with its square is that there's in principle there can be a problem for arranging transversality of the base locus, but essentially, so what does replacing L with its square do? It means that you're cutting by quadrics instead of linear hypersurfaces, and then it's a local computation that you can arrange transversality. Great. Are there, so you just sort of need enough dimensions to work in. Are there any questions about the statement of this theorem? Okay, so given this, now let me explain the strategy of the proof of the Riemann hypothesis. So let me remind you where we were. So here, x0 is going to be a smooth and projective even dimensional variety over a finite field FQ. And let's say the dimension of x0 is going to be, let's just say n+1. So the idea is we're going to be trying to prove something about the middle cohomology of x0. So we'll be doing some dimension, some induction on n here. So we want to do is we want to show that, so we want that the eigenvalues of the relative Frobenius on the middle cohomology, so on Hn+1 of x QL, we want them to satisfy that q to the n over 2 is less than alpha, so less than equal to is less than or equal to q to the n over 2 plus 1. Okay, and the idea will be to prove this by induction on the dimension. So first of all, so step 1 will be, without loss of generality, we can assume X admits a Lefschetz pencil. And we just every smooth projective variety over FQ bar admits a Lefschetz pencil. And moreover, we can assume this, this pencil which descends to x0. Can anyone say why that is? So Lefschetz pencil is some line. That line is defined by some linear form coefficients, and you can just adjoin those. You can just replace FQ with that finite extension, and we showed last time, or maybe last week, that the statement of the Riemann hypothesis was insensitive to extending your base field. So you can just replace FQ with a finite extension so that you get a Lefschetz pencil. And maybe just a remark. I mean, so when I defined a Lefschetz pencil, there was this kind of a specific form. Where was it? It was over here. There was a specific form the singularities have to take, and you can actually like pick your favorite quadric. All non-degenerate quadrics are isomorphic over an algebraically closed field. And so after a sort of harmless finite extension, you can assume all the singularities have your favorite fixed form. Okay, so step 2 is to you can replace x0 with the blowup of x naught along the base locus of the Lefschetz pencil. And what is this blowup? It's this family we wrote before. It's the same as x times L fiber product over L with the sort of family of hyperplanes. And this thing maps to L. So this thing is fibered, which is fibered over P1, which is a family over P1 write it this way, x naught in HT. Okay, so why can we make this replacement? Like, why is it enough to prove for the blowup? Well, one needs to compute what the cohomology of a blowup looks like. But the point is that the cohomology of the blowup is built out. So this is just a sketch, so I'm going to do all of these steps later. It's built out of the cohomology of x and the cohomology of the base locus of x intersect the base locus. And what is this? This is a codimension 2 variety. Right. So both of these are even dimensional varieties, right? So this piece we understand well by the induction hypothesis, and then this piece, well, if we can understand it on the blowup, we can understand it for x. So in particular, the key claim is that, the key claim is that the map blow up along the base locus uses from the cohomology of x to the cohomology of the blow. Okay, so the content of this is that we can assume that x lives in a family over P1 with very special fibers. So the generic fiber is smooth, and the singular fibers have unique singular points, which are all ordinary double points. Okay, so now let's look at the Leray special sequence. So we can assume. Let me write this. So we can assume we have x to P1, which is a so-called Lefschetz fibration. Which just means it's one of these families arising from a Lefschetz pencil. And let me call this map pi. 3. So step 3 is that now it's enough to understand the values of Frobenius on the pieces, on the parts of the Leray special sequence, kind of which are contributing to the middle cohomology of x. So what are those things? So those are H2 of P1 with coefficients in Rn-1 pi lower star QL. So remember, x was n plus 1 dimension, so contributes to the cohomology degree plus 1, and minus 1 plus 2 plus 1. Then H1 of P1 with our coefficients. So this is going to be the most interesting one. And then on H0 are n plus 1 of pi lower star of QL. Okay, so let me indicate how, let me call this A, B, and C, and let me indicate how we're going to approach each of these. Okay, so for A, we're trying to understand H2 of P1 with coefficients in Rn minus 1 pi lower star QL. Okay, so the amazing fact, which we're going to see when we study Lefschetz vibrations, is that this is actually going to be a constant sheaf. And this is not obvious. So why is this not obvious? I mean, this doesn't follow, at least immediately, from proper base change or from smooth and proper base change, because the fibers of this map are not smooth. They probably, and in typical situations, they will have some singularities, like there will actually be some ordinary double points. So the content of this is saying that the singularities don't contribute to this sheaf. And ultimately, that's a local calculation about ordinary double points, but we'll explain it later. So what does this mean? So this means, so how do you take the cohomology of P1 with coefficients in a constant sheaf? Anyone? So what this means, if you believe this, is that this is equal to Hn minus 1 of the fiber by minus 1. Well, sorry, here, there's a smooth fibers. Well, if we have a constant sheaf, we can use proper base change to compute what it is on one of the fibers. And then, well, what's H2 of P1? It's QL of minus 1. So we get cohomology of the fiber twisted by QL of minus 1. So this is a smooth fiber. Let me actually call this XT or something. Okay, so how do we understand this thing? Any thoughts? So is this something we can understand by induction? So let me remind you, the dimension of xt is n. Okay, so we can't use the hypothesis, and there are two reasons why. So one reason is that n is an odd number, and the induction hypothesis was just something about even dimensional varieties. And then two is that this is not the middle homology of xt, because n minus 1 is not equal to n. So does anyone see a way like one might be able to get into the situation where you have an even dimensional variety and you're looking at its middle cohomology? So the idea now is to let y inside of xt be a smooth hyperplane section. Which exists by Bertini. There's the field here. So I have to extend the ground field to actually get a smooth hyperplane section. That can genuinely happen. But again, the statement of the Riemann hypothesis is insensitive to extensions of ground field. And then by the Lefschetz hyperplane theorem, which will prove, I mean, I've sort of indicated something about this, the cohomology Hn minus 1 of xt QL will inject into Hn minus 1 of y with QL. And here y, so the dimension of y is n minus 1, because we've taken a hyperplane section of something n-dimensional. So this is the middle cohomology of an even dimensional variety. And we win by the induction hypothesis. All right. So are there any questions about this? So you have to think a little bit. So what you end up getting is, if you look at the eigenvalues of Frobenius here, we know by the induction hypothesis that they live between q to the n over 2 minus 1 and q to the n over 2 and q to the n over 2. And then when you twist by this minus 1, that all right. Are there any questions before I continue? So part B is the most interesting one. So this is H1 of P1 with coefficients in Rn pi lower star QL. And this uses the main lemma. So I'm going to discuss this next time, hopefully. But the strategy here is to try to understand this sheaf well. So this sheaf is here the fibers are odd dimensional varieties of dimension n. So this is their middle cohomology. This will have a skew symmetric pairing on it because coming from the cut product. So this is something that looks like something that we might be able to apply the main lemma to. Unfortunately, the monodromy for this sheaf in general will not in general be big. So it won't in general be all of SP2G, but there will be a piece of it where it's big. And so the strategy will be to break this into 3 pieces. So one of which we can apply the main lemma to, and then 2 others which will turn out to be constant. And then we can understand them via these kinds of techniques. Okay, so this is going to be next time. Okay, and then C, finally, we have H0 of P1 with coefficients in Rn plus 1 pi lower star QL. So in good situations, meaning situations we can arrange, this will also be constant. Okay, so again, it will be given by the cohomology of a smooth fiber, and then again the argument in A more or less goes through, so we win via an application of the Lefschetz hyperplane theorem plus Poincare duality. All right, are there any questions about this? So this is the strategy, and we're going to start executing it soon. So I owe you a few things. So the main things I owe you are, well, I need to prove the main lemma, which we're going to start doing shortly. We need to understand the monodromy of Lefschetz vibrations. So we need to understand in particular, why is this constant? We need to understand the Lefschetz hyperplane theorem, which we're using here. We need to understand this step. So in particular, that will involve an analysis of the monodromy on this sheaf. And then we need to understand why this is going to be a constant sheaf in good situations. So I owe you quite a lot. The first thing is going to be the proof of the main lemma, which maybe let me pause for 10 seconds if there are questions. And then if not, we'll start proving the main lemma. All right. Well, if there are no questions, let me begin. So let's start by proving the main lemma. Sorry, I've committed to writing the main lemma in all capital letters. Okay, so let's prove the main lemma. So what's the first thing we have to prove? So let me remind you what the setup was. So the main statement was we had, so here E naught was a locally constant QL sheaf on X naught with Frobenius actions having rational characteristic polynomial, a skew symmetric form C from E times E to QL of minus N, and big monodromy. So those were the three hypotheses. So here rational, let me just remind you, means rational characteristic polynomial. And then the first thing we want to prove is that E, so the representation associated to E naught, has weight N. So that means the eigenvalues of fx for x, the closed point of x, have absolute value q to the n times the degree of x over 2. And this is for any embedding of the field they generate over q into C. All right, so let's begin proving it. So we need two lemmas. So lemma 1 is going to be that if we take the 2kth tensor power of E, so this is the representation associated to our sheaf, and take the pi1 covariance, this is going to equal a direct sum of copies of QL to the minus Kn to direct sum to some big power. So this is saying the coinvariants of this sheaf are fairly simple. All right, and lemma 2 is going to be the following. So namely, we can reduce the statement about having weight n, so about these eigenvalues of Frobenius, to something about the radius of convergence of the zeta function of this sheaf. So namely, if for all k, the zeta function it should be E naught to the tensor 2k, has radius of convergence well, let's say, let me just write it, it converges for t less than 1 over q to the kn plus 1, then E has weight. Okay, so this is some analytic statement. Okay, so let me explain first of all why these lemmas imply this statement. Okay, so lemmas imply the main lemma part A. Okay, so here's a question. So okay, the strategy will be to show that lemma 1 implies that the hypothesis of lemma 2 holds, and then the hypothesis of lemma 2 immediately. I mean, the goal, what we're trying to show, is the conclusion of lemma 2. Great. So can anyone tell me why does lemma 1 imply imply lemma 2? So the claim, first of all, is that lemma 1 implies the hypothesis of lemma 2. So can anyone help me write out this zeta function in terms of, let's say, cohomology? Well, this zeta function of x naught, sorry, of x naught with the sheaf e to the tensor power 2k t, well, what does it look like? So it looks like some polynomial coming from h1 with compact support with coefficients in e, and then something with h0. So, and what are these somethings? The determinants of 1 minus relative Frobenius times t acting on h0 of the same thing. And then here's determinant of 1 minus f star t h2. Oh, sorry, this should be e to the tensor 2k here. And all of these things are e to the tensor 2k. Okay, so which of these affects the radius of convergence? So can anyone tell me about anything, any of these sheaves or any of these cohomology groups? Okay, well let's just look at this. So h0 compact support of x naught e naught to the tensor 2k is just going to equal 0 because x naught is assumed to be affine. So compactly supported h0 on an affine thing is always 0 unless the thing has a 0-dimensional component. So this is just 1. All right, what about h2? So let's look at h2 compactly supported of x naught e naught to the tensor 2k. Sorry, this should be of e, x and e here. So can anyone help me compute this? How would you compute h2 with compact support on a curve? So by Poincare duality,
Relate to h0, and then we're taking invariance.
yeah, so it's h0 of x e dual
Twisted by
2k
something.
twisted by 1 or minus 1.
We're taking invariance.
Right, it's twisted by 1 here, and then we're going to take the dual here, right?
Mhm.
Great. So this e dual becomes, well, let's actually do it. So this h0 is just the pi1 invariance, as Sasha said.
Mhm.
So this is, let me write it as e dual to the tensor 2k invariance dual, which is going to be e to the tensor 2k. Sorry, there's a 1 here. Maybe let me put the 1 outside. So the 1 goes inside the outer dual, but outside the tensor product. So this becomes e co-invariance and then minus 1. Great. Okay, so what does this say? So this, we know what this is. So this is by lemma 1. This is, well, the co-invariance of a tensor power of e we're just a direct sum of copies of QL of minus KN, and then we get a -1 from the twist by -1. So we get a direct sum of these things. So what does this say? It says that this zeta function of x0 e0 t is some polynomial coming from h1 over, well, now we know what happens from h2. We just get a power of 1 minus q to the kn plus 1 times t to the n. Okay, so that tells us what this is. Just because Frobenius acts on this thing by q to the kn plus 1. Okay, and now this thing evidently converges. I mean, if you look at the Taylor series expansion, it converges for t less than 1 over q to the kn plus 1, because this is the unique pole, 1 over q to the kn plus 1. So this satisfies the hypotheses. The hypotheses of lemma 2. And then the conclusion of lemma 2 is exactly what we're trying to prove. Okay, so now we have to prove lemmas 1 and 2. So unfortunately, I only have 3 minutes left, so it's probably best for me not to start them yet. Maybe I'll say a couple words verbally in the last 3 minutes, and then we'll do details next time. So this here is actually a purely representation theoretic statement about SP. So if you take the co-invariance of pi1, that's something that only sees the Zariski closure of pi1. Like taking co-invariance is an algebraic operation, so it's insensitive to replacing a group with its Zariski closure. And the Zariski closure is all of SP2G. So this is a statement of saying, so suppose you take the standard representation of SP2G, look at its even tensor powers, can you write down the invariance in terms of the symplectic pairing? And the answer is you can, yes. So I'll explain that next time. And then this is like follows from the product formula. So you write this as a product over the you write the zeta function as a product over the fq to the k points of x0, and then just stare at what it means for the radius of convergence to be what you think it is, or to look like this. And so both of these. So here this is a non-trivial but essentially elementary statement about representations of the symplectic group, and this is like elementary complex analysis, I guess. So we'll do those next time, and then we'll move on to part B of the main lemma. All right, are there any questions before I stop recording? Well, if not, thank you all for coming today. There will be no class on Thursday because it's Thanksgiving, but we'll pick up next week. And I have to figure out if there's going to be class this coming Tuesday, because I think UGA has a, if I remember correctly, they have a Friday schedule this coming Tuesday or something like that. But I'll check and post something on the Discord. All right, happy Thanksgiving, everyone who celebrates it, and thank you all for coming, and have a great break.